Kriging is in some respects quite similar to inverse distance weighting. But it's simply that the difference here is simply how the weights are calculated. And for this we use something called a semi-variogram or variogram. The terminology is a little mixed. You can annoy people by using the wrong word if you like. It doesn't matter. And this method also relies on all the data. In the previous example with inverse distance weighting, we said quite often we will define an area of interest for us. Don't look beyond this area, but all the data within it is of interest. Whereas Kriging typically will use all available data because it requires a lot of data. This is also where we come to one of the downsides of Kriging as well. But the basic concept of it is the question, as it says there, how different from me can another point be? How different can I tolerate that new point that we're going to calculate? How different from me should it look? And again, it's following Tobler's law. The farther away from me something is, the more I can accept it being different. The closer it is to me, the more like me it should be. It's the same basic concept, but how we come about this to the weighting and this decision of how different it is different is shown here. So what we do when we create this variogram or semi-variogram is we look at the variance within certain distances from points, data points. So here we've gathered data points. Each of these marked it shows an elevation, and we start by taking a point. We're going to go through every single point in our data set. We're going to do this analysis on every single data point. So we start here, and we can see that there are different so-called lags. They're called lags in Kriging. So we go out to a certain distance, different bins, if you prefer that terminology from say, a histogram. So we say everything within this area is one lag, and then everything within this ring here is another lag, and everything within this ring here is another lag, and so on. And we calculate then the variance of all the data points within those lags and plot that variance onto our variogram. So first lag, we calculate the variance of all the data points in that, and then the next lag, we calculate all the variance within that lag and plot it here. And then lag by lag, we calculate the variance, we gather in all the data points and look up the variance within those, and then plot it on this semi-variogram. So for each lag, what's the variance? For each lag, what's the variance? Around that point there to begin with. And then once we've done that, we move on to the next point and repeat. We do exactly the same thing. So we look at the lags, calculate the variance within each lag, and then we plot those onto our semi-variogram. And then once we've got all of our points done, once we've covered the whole of the data set and calculated the variance within each lag from each point, we can then draw a best fit line in some way through our variogram. And this represents the theoretical model for how the variance changes with distance from a point. So when we're standing at a point, whichever point we're standing at, and that could be any point that isn't even defined here, it could just be some unknown point, and that's actually the whole aim of this exercise. And then we can say, well, with increasing distance, the variance will increase. So I can accept larger changes. I can accept larger differences. The fact that it goes up and down, yeah, I can accept a bigger and bigger difference up to a point. And then at some point, it stops. Well, the variance isn't going to increase forever. We're not going to go to infinite variance. At some point, the variance will stop, and we're going to be within a certain range of values. This is, technically speaking, within Kriging, actually not the value of the surface, but it's the differences between these elevation points. It's a technical detail. Don't worry about it for now until we really get into Kriging. But this is the essence of how to sort of think about it. So we've created this model, and now we want to create a new value here. We want to put a value on that point based on how different can this point be from all of the others given this model? So the nearer I am to a data point, the less I can vary from it. I've got a certain range of values I can assume, but I can't go to any extreme. I need to be within a certain amount of variance. And then if I go to the next distance, from this point way over here, I can accept a value. The new value here can have a certain difference from that. It can be, there's a lot more flexibility. I can assume a value here that is quite a lot different from that, or not very much at all, depending. Depending on how we solve this. And we do this for all of the data points, and we find out what the best solution, how do we best satisfy all of these demands. So this point doesn't want any more variance than that. It should be somewhere around there. That's what it should look like, approximately. And here it should approximately look like that. But we're going to sort of fit it in, given all of these data points, what they can accept, how much variance from them can they accept. The problems here with Kriging, there are many. We have this curve to draw. How is that curve drawn? What's this? I mean, there are terms for this. You know, we have the sill and the nugget and the lag and so on. This is a very detailed method. But when we drew this curve, we can just drew it through there. We could draw a different curve and get a different result. We have a certain amount of variance that is unexplained here. This is called a nugget because this comes from the gold mining industry in South Africa, and so the idea was that this would indicate a nugget of gold approaching in your samples. You can read up on the details of that if you want on your own. Let's not worry about it here. Let's just say that we have a model that fits the data, and how do we know that that is actually the best line to fit the data? How do we know that our data is actually correct over the whole of our spatial domain? How do we know that the statistical model that we're using to build this up is correct? There are variations, especially when it comes to elevation. How do we know that changes in elevation are due to one particular process rather than many different localized processes? We have the geology of the area, we have tectonic uplift, we have hydrological processes that may be eroding and sedimenting out layers in particular places. We have slope processes where masses might be slumping down or wasting. So we have several different processes acting in an area with different spatial regimes, different statistical descriptions. How are we going to get all of that into our statistical data? This is where Kriging can actually be quite problematic and doesn't always work. In fact, I'm personally of the opinion that it works in very few cases. But it looks nice. The results tend to look really quite nice. The triangulated irregular network. This is a popular vector-based method whereby instead of creating a raster, we have a series of nodes, these points, connected by lines to build triangular facets upon which we can do a linear interpolation to find a new value for every single point on that surface. But the only information we need to store are essentially the node points and the connections between them. So we do a Delaunay triangulation and then create this tin. And then here, so we have information on these points, and we say that these were the points that are connected. And if we want to create a new or find out what the value of the elevation there or whatever this is representing, well, then we can do a linear interpolation based on all of these three lines, and we get a new value there. This is a very popular method because it's quite flexible. We don't need to store data where it's not needed. This can accommodate rapid changes by putting in spatial changes, by putting in lots of data there, and then where not much happens, we don't need to record much data. We just have a large triangle or triangles, larger triangles covering this dull surface where not much happens. So we can adjust our data density accordingly, which is quite nice. And it also tends to provide a reasonably intuitive understanding of where things are happening as well, where we have this requirement for data density. So if we try and compare these rather crudely and incorrectly, but let's just see what happens. Here we have a DEM in the background, a reasonably high accuracy DEM, and here we have an ESCA running through this. It's been dug out in a couple of places historically. We have a river running through here. We also have a drainage ditch coming in there, but I've just simply thrown out some random points over this area. I didn't, I asked the GIS software to do it for me. So these red dots are randomly located points, which is not the ideal way of doing a survey, but let's just see what happens. And when we do inverse distance weighting from these points, we get this pits and peaks image, trying to recreate that ESCA there. It's not great, and that's more a feature of the data density. But also we can see there's some effect of the inverse distance weighting in this. It creates this unpleasant effect. The Kriging, we get these nice smooth surfaces. Is that any more true? That's also questionable. We don't get these pits and peaks as much, but well, that didn't really work out any better, just differently bad. And then the triangulated irregular network, arguably the best result, even if it looks the least natural. We are sort of picking up on there being a feature running through here like this, but that's also, that's a matter of interpretation and personal taste, I think. But we can see that all three of these methods do things differently. We come up with different results. Which one is best is really going to depend on the situation and the data we're using. And that's what we were aiming for, just to remind you.